So how would we do an implicit search of a tree? Build the tree on the fly. So here I'm going to have a little code called decision tree implicit. And I'm going to have a similar kind of thing. I'm going to call it to consider and available. It's just like so far and to do. To consider is what are the things I still have in my list I could hand in. But whereas in the previous case, so far was all the set of things I had, here I'm actually going to keep track of how much space is still available. So it's doing that test to see, do I still have things available or not? What I'm going to return is the value of the solution and the solution itself. So what does my process say here? It says if there's nothing left to consider, or if there's no more room left in here, the result I'm going to return is just a value 0, and there's no solution. I can't do anything here. Otherwise, I'm going to take the first thing into consider, and I'm going to get out the weight of that. And if that is, in fact, too big, it's bigger than what's currently available, then my result is simply whatever I would get by solving the rest of the problem, not including that element, right? So starting with everything after that element into consider, but still with the same amount of room left. The difference I have here is that available is keeping track of what's left. In the previous case, I ran the computation every time of using that function of what was my constraint in order to make sure that I was okay. All right, so solution there says nothing. If I've got nothing left to consider or there's no room left, this one says if I don't have room left, I'm going to find a solution without including that object. Otherwise, I'm going to take the next item out, which is the thing out to consider, and I'm going to find a solution where I include it and a solution where I don't include it. So notice what it says. It says I'm going to bind with value and with to take to be what I get by doing the same search, where I do it not including that item, but where what I have left is reduced by the amount of space this would take. It's finding the solution to the subtree below it, and then I'm simply adding that item in. I'm going to find a solution where I don't include that item, and I therefore have the same amount of space available. And then finally, I'm going to say, gee, if the solution with it is better than the solution without it, there's my result. Otherwise, there's my result. So what this is doing is walking its way through the tree, exploring it each time, stopping if it gets to a point where there's no more room available, perhaps there. And in each case, when I do have room available, finding a solution with it, finding a solution without it, and then using this test to decide which is the best solution in order to pass that all the way back up through the tree. If I were to do that, I, in fact, can find a very nice solution. So let me, for example, using that code, say I'm going to let val and taken be what I get by doing dt implicit with my stuff, and 10, that was the size I had. And when I get that out, there's the value, and there's the things that I took. But this, in some sense, is cleaner code. It's easier to see how I'm making the decision at every point. And so rather than calling the function to say, what do I have left, I'll just keep track of what I have left. And rather than then worrying about doing all of the construction of the full tree before I explore it, here I'm only building the tree as I need it. So that now lets us see depth first and breadth first search, both finding whether an element's present, finding a path to it, and then generalizing that idea of finding a path to actually make decisions to find a solution to a kind of optimization problem. That tool you're going to find really useful in many other places.